Hey everyone, welcome back to Science Sketchbook. This video will be part of a series on addition reactions. I'll be covering the regioselectivity, stereoselectivity, and mechanisms with the most common reagents for these reactions. Here we are starting with the various options for hydrohalogenation. As a brief reminder, for the addition reactions we are covering here, you'll be adding atoms along a pi bond. As well, the region and spatial arrangement of what's added on is sometimes specific to each reaction. Oh, and before we hop right into it, we've got a bark reminder from Sketch. The background and review knowledge you will need for this concept involves carbocation rearrangements, specifically the hydride shift, methyl shift, and ring expansion. Hydrohalogenation reactions form carbocations. And remember, every time you've got a carbocation, it can swap places to become more stable. So, here's what's on the agenda. We are going to be covering these three scenarios. Just your standard hydrohalogenation, hydrohalogenation in water, and hydrohalogenation in an alcohol. So you're going to see that these solvents really cause an impact on our final product. So the main reagents we will use include the following. Option 1 is just the standard hydrohalogenation. As the name of the reaction suggests, this is where just the hydrogen and the halogen get added on to that pi bond. And the halogen, often represented with X here, is something just like chlorine or bromine, for example. Option 2 is where the solvent is water. In this case, the halogen will be cheated of its spot. So instead of there being a halogen on your final product, OH is going to take its spot instead. And a little tip for you, anytime you see water in these addition reactions, that's a good sign that your end product is going to have an OH on it. And option 3. This is where the solvent is an entire alcohol, like methanol, for example. Now notice with this one as well, the halogen got outcompeted by the solvent. So it's kind of just like having water, except on the end product, you're not going to just leave an OH, you'll add on that entire carbon and oxygen group of whatever alcohol you're given. So let's focus on our standard hydrohalogenation. Before I show you the mechanism, I think it'll be important for me to give you context to what exactly we're going to be forming in the end. So let me show you the what, where, and how of the atoms that will be added on in this reaction. So what's added on? Just the hydrogen and halogen along the pi bond. Check it out in this example here. Notice that at some point that double bond will disappear and you'll just be adding on a hydrogen and a halogen. All right, now where do atoms add in this reaction? Well, this is a Markovnikov reaction. That means the priority group, which is your halogen here, will get the more substituted, more stable side of the pi bond, which I basically refer to as the good side of the double bond. You can see it highlighted there. Now, how will they add on? Well, in this reaction, they don't approach from any particular side. In other words, this reaction isn't stereoselective. It'll neither be syn nor anti. You'll form a mix of products with wedges and dashes and such. But do keep in mind that this reaction forms a carbocation. And that means that that carbocation can rearrange as it tries to find a more stable spot in the molecule. All right, so that's just the general overview. No worries if you feel kind of overwhelmed at this point right now. This was just context, so you know where I'm going as I show you the mechanism. I know words are just words, so let's see it in action. I'm going to show you the arrow mechanism or steps to each scenario. So starting with our standard hydrohalogenation, let's work with this substrate here, 3-methylbutene. If we react it with HBr or hydrobromic acid, we are expecting an H and a Br to be added somewhere on this molecule. Let's see how that's accomplished. Well, the first thing you might notice here is that bromine is more electronegative than hydrogen. So that creates a dipole here, where hydrogen becomes kind of partially positive. And what tends to seek out something positive? Well, electrons do. The double bond here is an extra pair of electrons, right? So it's basically going to just swing open like a door and grab onto that hydrogen, disconnecting it from the bromine. Since this is a Markovnikov reaction, the hydrogen is going to attach to the less substituted, less stable side to leave room on the better, more stable side for the halogen. Since that double bond door swung away from that second carbon there, It lost a bond, right? So that creates a vacancy or a carbocation. This in itself explains why this reaction's Markovnikov. If we're forming a carbocation, we got to form it on the more stable carbon. We don't typically just form primary carbocations, right? That's pretty unstable. So at this stage, the hydrogen is just basically another implied hydrogen at this point, so you don't even really need to draw it in. It would be more important to include it if the stereochemistry was going to matter later on, but since it doesn't, you can just ignore it for now. All right, let's see. Oh, remember Sketch's bark reminder earlier? Whenever you see a carbocation, it can rearrange to become more stable. Being secondary isn't so terrible, but do you see a better spot for that carbocation on this molecule? Yeah, just to the side, there is a tertiary position. If only it was there, right? Well, there's a solution for that. The hydrogen that's sitting there can swap places with the carbocation via a hydride shift. Hydrogen doesn't care to be somewhere more stable. It'll gladly move over. So, yay, it is now on a more stable tertiary carbon. At this stage, that carbon has become sp2 or a trigonal planar now. So, any wedge or dash that was present there will actually just look like a planar line. Okay, now to complete the addition, that bromine needs to come in for the attack. What do you think? Will that bromine approach from the front or the back? Well, you can't really tell with a carbocation. It's planar, so there's nothing kind of sticking out in any direction blocking you. Then, since it can attach from either side, it'll do both. That should explain why this reaction is neither syn nor anti. That bromine isn't required to be on the same face as the hydrogen earlier. So let's see the arrow. Check it out. Bromine can approach from the front, forming this product here. Or it can approach from the back, forming this other product here as well. So why is that important? Well, if these molecules were chiral, you would be forming a racemic mixture of enantiomers with, one wedged and one dashed. So taking a look at our original substrate, if we react it with hydrobromic acid, we will get these products here. And that's it for this mechanism. So you might need to watch through that a couple of times to get used to it, and of course with practice it makes more sense. So that standard scenario is taken care of. Now, what'll happen when the solvent is water? Well, it basically becomes an acid-catalyzed hydration at this point. Let's see how it differs. So what will be added on? This time it'll be a hydrogen and a hydroxy group, or OH there, instead of the halogen. Look at this example. Notice how the halogen never ends up on the final product. Once again, water is just pretty selfish and will come in and take its place at the last second. As you might be able to tell, this is still a Markovnikov reaction, so that hydroxy group will be getting the more stable, more substituted good side of the double bond. And once again, this reaction is not stereoselective to syn or anti, it'll form all products. But once again, it does form that carbocation, so keep an eye out for rearrangements. Let's try it with the same substrate so you can easily compare them. Well, the mechanism is going to be pretty identical. It's just that instead of bromine adding in, the OH will sneak in at the last minute and take its spot. Since those first few steps are the same, let's go ahead and just fast forward through what we've already covered. So double bond opens up, forms carbocation on more substituted side, and it rearranges to that tertiary carbon. That leaves us at this stage right here, where we've got the carbocation ready for the addition. All right, look at that bromine. It is eager to go and attack just as expected. But oh, water comes in and steals its spot. Poor bromine, man. Our expected hydrohalogenation has just basically become a hydration at this point. So it is what it is. Water is going to end up on our product here. And of course, since the reaction is still not stereoselective, the water will approach from both the front and the back, just like before. So we're just about done with this one, but the products look a bit messy, right? You don't usually just leave water with, a charge on it just hanging off a molecule like that. So you can go ahead and just deprotonate it to clean it up a bit. Basically, something like the water can come in and just kind of pluck that extra hydrogen off, getting rid of that charge there and leaving you with just the OH. Now let's look at it again with that original substrate in view, and you can see that the bromine in that hydrobromic acid didn't have a chance. Now, the hydrogen did the dirty work of opening the double bond, so at least he got to end up on the final molecule, but once again, bromine didn't get its big finale, and it was outcompeted by the water. So we just finished that situation where the solvent water messed with our anticipated hydrohalogenation product, right? So what do you think happens with a full alcohol with carbons on it? It's basically going to be the same situation, but instead, the entire alkoxy group of that alcohol solvent will outcompete the halogen instead. So note that it's not just the OH at the end there, it's the entire carbon and oxygen part of the molecule. And once again, our priority here, which is the alkoxy group, will get the more substituted good side of that double bond. And finally, once again, not stereoselective, neither syn nor anti, but may rearrange because of its carbocation. So let's look at that mechanism. Once again, it is literally the same. I don't really think Sketch wants to go through it again. So let's just kind of look at the main idea of these products here. We've got the same substrate and still using hydrobromic acid, this time in methanol. So once again, bromine is a huge loser and gets cheated out of its spot. Now this time by the entire alkoxy group shown. So this basically just forms an ether. And that is that. So to recap hydrohalogenation, check out the summary on the left. It is a Markovnikov reaction where stereochemistry didn't matter. You just had to worry about rearrangements. With just a hydrogen and halogen, the halogen will be the priority that gets the good side of the double bond. If this reaction occurs in water, an OH will actually add on to the good side instead. And if this occurs in an alcohol, you just put on the entire carbon and oxygen chain of that alcohol instead too. And if you're more of a written word type person, here are all of the steps of the mechanism typed out too. 1. The double bond opens up and grabs the hydrogen. 2. This adds the hydrogen to the less substituted side and leaves a carbocation on the Markovnikov side, or the good side. 3. Then, check if that carbocation will rearrange. 4. Add the halogen to the carbocation. And if present as solvents, you might have to add an OH or an alkoxy group instead. And 5, finally, the wedge and dash position of the atoms added on don't really matter. You'll form both because this reaction is not stereospecific. Phew, that was a lot to say, huh? So, time for some practice. I just want you to find the product of these hydrohalogenation reactions. As always, Sketch suggests you pause the video here to practice. I'll give you a moment and we'll come back for the answers. And here we are. So, did you get them right? For the first one, the chlorine did indeed get the Markovnikov side. But if you're confused on why the shape is so different, you may have forgotten to rearrange. The type of rearrangement here would have been a ring expansion. For the second one, remember, with water as your solvent, it'll steal the position of that halogen. So that's why your final product ended up with an OH bonded instead. By the way, the carbocation formed in this reaction was as stable as it gets in this molecule, so there was no need to rearrange. Now for the third one, the whole ethanol was added on and deprotonated to basically make this ether, right? Once again, if you're confused on the shape, this one also did a rearrangement. The carbocation formed was secondary, so it did a methyl shift, allowing the carbocation to be on the tertiary position instead. So that might have been pretty tough, but I know you did an amazing job, and for these concepts, practice always makes perfect. If you need any extra clarification, feel free to drop a comment below. Otherwise, it could be good to re-watch the mechanism to get the hang of it. Alrighty, and that is the end. Thanks so much for watching. If you want to keep supporting my content, feel free to subscribe. Otherwise, hope to see you again soon. Bye!